Salam sejahtera and a good day. In this section, we shall be comparing two groups using t-tests. Parametric tests such as t-test, ANOVA, etc. can only be performed on data sets that fulfill the following fundamental assumptions. Number one, data is normally distributed. Number two, variances of the populations should be approximately equal. And number three, no extreme scores among the data set. Variances of the populations should be approximately equal, or also known as the principle of homogeneity of variance, is important because we should not be comparing two populations that are not the same to each other. Imagine comparing the height of a group of human beings versus a group of giraffes. And this is also the reason why we need equal number of samples for comparison. Extreme scores will distort mean, standard deviation, and standard error, and therefore should be avoided before we perform parametric tests. The test is actually used for two-group comparison, provided that the sample distribution is normal. However, we often assume that our sample distribution is normal and take things for granted. In order to make sure that the data sets are normal, we need to perform tests such as Kolmogorov-Smirnov or Shapiro-Wilks test, or a simple probability observed or expected distribution plot in order to actually ascertain that our data sets is parametrically is conforming to normal distribution and therefore fit to be analyzed using parametric statistical tests. And if, let's say, the principles of normality are not conformed to, the data sets should be analyzed using non-parametric statistical tests. The t-test operates on the theory that there is actually a statistical significant difference between two means. The two means are in turn derived from two groups of sample. For example, you may be dealing with a group of control rats versus rats treated with drug A. And then there are also two types of t-test, which are paired t-test and independent t-test. Paired t-test is used when different sets of data are measured from the same or related subject over time or over experimented setup. In statistical terms, it is meant for populations with equal variances. It can be used to reduce effects of confounding factors as samples are essentially matched to each other. For example, cholesterol levels before and after a treatment, or effects of vitamin A on retinal functions in twins. The independent t-test is used when subjects from two groups are unrelated, and therefore the name independent t-test. For example, effects of drug A versus untreated control on levels of liver metabolite in two groups of rats. T-tests also allow us to test the effects as one-tailed test or two-tailed test. One-tailed test is used when all changes occur in one direction only. Let's say either positive change or negative change only. Two-tailed tests are used when changes occurs in both directions. For example, there could be both positive or negative changes after a treatment is applied to the experimental population. Look at the following example. The following example showed serum cholesterol levels with units deleted from 24 experimental subjects who were on standard American diet and then switched over to a purely plant-based diet for 1 month. Serum cholesterol measurements were done before and after plant-based diet. Formulate a hypothesis and test whether plant-based diet produces significant changes to the serum cholesterol level. Assuming that we are conducting this experiment at 95% confidence level, then if we key in the data, we can actually analyze it in multiple ways. Let's look at how we typically approach it using the manual method. To perform the t-test using the manual method, the first step that you need to do will be, of course, to check normality using the test indicated earlier. Among them, Kolmogorov-Smirnov or Shapiro-Wilks test. And then once the normality is ascertained, it becomes important for us to perform the test using paired t-test procedure. Using manual method, refer to the formula on the top right, then you calculate the paired difference and use the paired difference to calculate average difference and the difference SD and the SD of the difference, and ultimately the t-value itself. And once you got the t-value, compare the calculated t-value with critical t-value at the appropriate alpha and degrees of freedom from a t-value table. And based on that, interpret whether the alternative hypothesis or the null hypothesis is accepted based on the t critical value referred from the t table. However, I would suggest that the easier way will be to run the data using the SPSS software, where all these t-critical, t-test value will be compared and analyzed automatically against the established t-table. If you key in the data in SPSS, do note that for t-test, this is independent t-test, this is actually how you should key in the data. In this case, you have the before and the after column. Do note how data is being keyed in if you are performing a paired t-test versus an independent t-test. And activate the menu within the SPSS by clicking Analyze, Compare Means, and then choose Paired Sample t-test. And once you brought up the menu on Paired Sample t-test, put in all the analytical variables into the respective pairs of variables, variable 1 and variable 2 as indicated here, and then click OK. You shall be presented with the following results. The first table indicates to you what will be the mean before the trial and the mean after the trial. In fact, the first table within the t-test output is a table that you should be paying attention to, because it will tell you whether all experimental subjects are taken into account or otherwise. In this case, we can see that all 24 before data and all 24 after data are all taken into account. And from here, you can also see what will be the mean, the standard deviation, and the error of both the before trial values and the after trial values. On top of that, we can also have the correlation between these two values. These correlation readings will actually tell you whether these two subjects are actually, two groups of subjects are related or not. In this case, they are related because the values are coming from the same person. And therefore, it's right for us to use the paired t-test model. How to interpret these results then? Well, in order to interpret the results, we need to know the mean difference between the before trial and after trial. So you can see here, 187 minus 168, you'll get roughly about 19.54. This is actually the difference between before trial and after trial. And in order to know whether this difference is actually significant or big enough, we need to look at the significance for a two-tailed t-test. So in this case, the probability of the significance two-tailed test is actually less than 0.0001. So in this case, since it is actually less than the critical value of p.05, significance value of 5%, or p equals 0.05. So we could say that the difference of 19.5 is statistically significant. Do bear in mind that we are actually testing this statistical significance at 95% confidence level. Do recall that if the value is less than 0.05, then the difference will be statistically significant. If the values are more than 0.05, which is corresponding to 95% confidence level, then they are not statistically significant. Moving on, let's look at independent t-test. Look at this example. An experiment was done to examine effects of drug A on the liver metabolite level versus untreated subjects in rats. Group A, comprising of 20 rats, was treated with drug A, and group control, another 20 rats, was the untreated control. Recall that this model is different from our earlier paired t-test model, whereby we are using the same subject for before reading and after reading. In this case, in the independent t-test, you do know that whatever is actually happening in group A animals will not affect the control animals, and therefore independent t-test is indicated for this particular analytical model. So the values for group control and group A are depicted respectively here on the slides. Formulate a hypothesis and test whether drug A produces significant changes to liver metabolite level in rats. It becomes important for us to formulate a hypothesis for the independent t-test. So, as usual, the null hypothesis will be group control and group A are not different from each other. And the alternative hypothesis will be the mean for group control and group A are different. The manual method used to perform this independent t-test will have to take into account few considerations. Of course, as usual, number one step will be to check normality. And then after that, proceed to check and analyze using independent t-test procedure. The first thing that you need to do will be to determine whether the variance and samples are equal and decide on the right formula to derive the appropriate t value. Which is why this test is known as the t-test. Assuming you have equal variance and equal sample size, then you use the following formula and reject the null hypothesis if the t calculated is above the t critical taken from your t-test table, but accept null hypothesis if the t calculated is less than the t critical value. This is the t table that you need to refer to in order to analyze this. The t table is read according to the degrees of freedom, that means sample size, and of course, according to the number of alpha here, the significance level. In the second scenario, whereby you have equal variance but unequal sample size, then the formula will be slightly modified for this particular purpose. Note this, all these text in red. In the third scenario, you might have unequal variance with unequal sample size. This is a special procedure whereby you, instead of using a routine t-test, you may need to use a Welk t-test. However, under such circumstances, I would advocate that I would suggest that you really need to look at your data again and see where is the source of unequal variance and unequal sample size. Analyzing the data under this kind of condition will require you to know extensively about the background of the data collected, just to make sure that you are testing things on the right track. So based on that, you can see that there are also modifications done to the t value here based on either differences between the two groups divided by the estimated standard deviation of the two groups. The same principles applies here of either you accept or reject the null hypothesis. If you perform this using SPSS, you don't have to consider all those three possible potential considerations because it's all built into the SPSS, even though you may need to take what type of test that you're going to analyze later. As usual, if you're going to perform the t-test analysis, independent t-test analysis, you should be checking for the normality of the data sets. And then and only then, subject the data set to independent t-test procedure. If you are analyzing using SPSS, there will be an automatic Levene's test being included. So we shall be looking at what is the purpose of Levene's test and what does it do. And for a note, in a later stage, when you start your non-parametric test lectures, please compare the results from this particular lecture with that of the Mann-Whitney U-test, which is actually known as a non-parametric t-test equivalent when the data is not normally distributed. Assuming that you are using SPSS to run your analysis, do note from this particular slide how the data sets are being keyed in if you are performing independent t-tests. Bear in mind that if you are running independent t-tests, the data sets are being keyed in differently. If you are analyzing this using a paired t-test model, the before value and the after value are being keyed in side by side. However, if you are running an independent t-test model, you need one column to designate treatment group and another column to designate the outcome or the dependent variable. So it becomes important for us to know how to designate this and how to put this one in when you are looking at through the variable view of the SPSS software. You have to make sure that you have entered the data correctly, and then and only then you can perform independent samples t-test. To invoke independent samples t-test, as usual, you go to the Analyze tab, click on Compare Means, and then click on Independent Samples t-test. And once you have the Independent Samples t-test, you get this particular menu. And from the menu, make sure you shift the test variables, which are actually the dependent variables, in this case, named as metabolites, into the test variables, whereas the independent variables will become the group variable. And do assign what is the number that you use to represent the various treatment groups within the independent variables, in this case, known as TRX or treatment. There are only two groups because we use numbers 1 and 2 to designate the two groups. Of course, you can have a multitude of groups over there, 3, 4, 10, but only two groups are only going to be analyzed at one time, depending on what you assign for that particular grouping variable assignment. Once all these are done, click OK, and then you should be able to get these type of results. Same thing again, it becomes important and customary for you to look at group statistics. This table on group statistics will tell you how many variables are actually entered into this particular analysis. So this should be your focus at the beginning of every interpretation. And then once you have this, it will also allow you to read what will be the mean for the untreated control, the mean for the group A, their standard deviation, and the standard error of mean. Based on this, how do you know whether the differences between the untreated control and drug A treated animals are actually different or not? Because based on the group statistics, you know that untreated control has a mean of 15.5, whereas animals treated with drug A had 17.9. So is this difference significant or not? In order to know that, you have to read the independence sample test table. Do note that there are two rows of values here. The first row represented by assuming that all the values are conducted under condition that equal variances assume. The second row assume that the values are derived based on data that had equal variances. They are not based on data sets that do not have equal variances among them. As you can see here, the way to interpret this table is that if, let's say, the data, the equal variances are not assumed, then you need to switch over to interpret values from the second row. Now, how do you know when to use the first row and when to use the second row? This is actually where the Levene's test of equality of variances comes in handy. Levene's test will actually allow us to check whether the variances are equal or not. This is actually the second assumption that you need to ensure that you are adhering to before interpreting results from t-tests. Remember the three principles that you need to adhere to before utilizing parametric tests for data analysis. Number one being that the data is normally distributed, which you normally should, by now, you should be able to perform and ascertain that the data is normally distributed. Principle number two is that the variances supposed to be equal, which is actually being tested using Levene's test here. And of course, number three, no extreme scores among the data sets. So in this case, how do we know that the equal variances assumed? It is important for us to look at the significance value, which is within the Levene's test. We wanted a non-significant value here, meaning that we wanted a value that is more than 0.05. If the values that are more than 0.05, then we should be able to read all results within the first row. If the values are less than 0.05, then we should be reading results from the second row. In this case, we can see that the next cluster of values will actually tell us whether the t-test comparisons are statistically significant or otherwise. So we will know that by reading the two-tailed significance for the t-test in this case. So in order for the differences to be significant, this this probability for two-tailed significance value should be less than 0.05. So in this case, you can see both are less than 0.05, regardless of whether the variances are equal or otherwise. So it makes no difference whether we're interpreting the values from the first row or the second row. The crucial thing here is that we do know from this particular result, our data from drug A treated animals and untreated controls are statistically significant at 95% confidence level.